All right, so here are just a few more 3.11 problems. Remember, this is just derivative of hyperbolic functions, and they work the same way as the trig functions, okay? So like, let's say you had hyperbolic cosine cubed of x. So this is still the power rule with the chain rule, right? Like if this was cosine cubed of x, how would you do it? You would derive the power first. So that's what we would do right here. So as far as the power rule, well, I will use a different color for this right here. Remember, the power rule would state, oh, we have to take that 3 and put it out in the front. And this becomes hyperbolic cosine squared of x. So we've only derived this cube portion, the exponential portion. Now we need to continue chaining, right? We have to go out there and derive the cosh of x, right? So what's the derivative of hyperbolic cosine? It is just the hyperbolic sine of x. And then if there was something else besides x in here, like x squared or something else, right, we'd have to sit there and derive that through the chain rule and get 1. Or we'd get 1 in this instance. So don't forget, you always have to chain the inside, right? So first, I had to do the power rule. So 3 hyperbolic cosine squared of x. Then we were done with these powers. We moved to the next internal piece, which is the hyperbolic sine. The derivative of the hyperbolic sine, the derivative of the hyperbolic cosine is hyperbolic sine of x. And then lastly, we derive the inside of that trig function x, what's remaining, and we get 1 right there. So that's where that 1 comes from. And of course, you don't have to put the 1. This would just be the final answer, right? 3 hyperbolic cosine squared of x times hyperbolic sine of x. What if you had, something like this? Secant squared of, and I'll say e to the 5t right here. Very similar, right, to this first one right here. We're going to have to chain it a few times. We start with the power rule. So what do we need to do? We need to take that 2 and throw it out in the front. So we have 2. And then secant to the first. And then of the inside, right? The inside has not changed. So we're done with the power rule. We took care of that squared, but now we need to move to the derivative of the next piece, which is this secant, hyperbolic secant, right? I forgot to put that h there. Put the h. Now we need to derive the secant component. Remember, what is the derivative of hyperbolic secant? It is negative hyperbolic secant of the stuff times the hyperbolic tangent of the stuff. Damn. So we've derived, remember, this is the derivative of hyperbolic secant, this chunk right here. But now we need to derive the inside of it finally. So the derivative of e to the 5t, because that's chain rule. Remember, the derivative of e to whatever is e to whatever times the derivative of whatever. So what's the derivative of 5t? It's just 5. So what is the final answer in this case? 2 times the negative sign times the 5 is negative 10. Then we have, since we have 2 secants, right? We have 2 hyperbolic secants that we're multiplying together. We could say, oh, that's a hyperbolic secant squared of e to the 5t. And then lastly, the tangent, hyperbolic tangent of e to the 5t. Again, where did I get this squared from right here? It's because you had hyperbolic secant of e to the 5t times another hyperbolic secant of e to the 5t. So we could say that's hyperbolic secant squared. From this negative sign, where did it go? Out front. 2 times this 5 here gets you the negative 10. What if we had y equals 1 plus hyperbolic cosine of x over 1 minus hyperbolic cosine of x? So we're dividing, and we have to derive. How are we going to do that? With the quotient rule. Remember the quotient rule, you had f and g. Now remember the quotient rule was you had gf prime minus fg prime over g squared, right? So that's what we have to do right here. So let's take our time with it, right? Because it's very tedious, lots of little places where we can make mistakes. G times f prime. Well, g is 1 minus hyperbolic cosine of x times the derivative of f. What's the derivative of 1 plus hyperbolic cosine? Well, derivative of 1, 0. Derivative of hyperbolic cosine is just hyperbolic sine of x minus f times g prime. F is the 1 plus hyperbolic cosine of x times the derivative of the bottom. Derivative of 1 is 0. Derivative of negative hyperbolic cosine of x. Well, if I block the negative out for a second, remember, what's the derivative of hyperbolic cosine? It's positive hyperbolic sine. But since there's a negative out in the front, it's just negative hyperbolic cosine of x. And that's all divided by 1 minus hyperbolic cosine of x squared. Right? Because we have to square the denominator when we do the quotient rule. So can we do anything with this right here? Well, let's, distribute and see if we can combine like terms. We can distribute this hyperbolic sine into both of these, just like this right here. So we have, this becomes hyperbolic sine of x minus hyperbolic cosine of x hyperbolic sine of x. And then negative times a negative is a positive, right here. So we're going to have plus a hyperbolic sine of x, and then we're going to have plus a hyperbolic cosine of x, hyperbolic sine of x, all divided by 1 minus hyperbolic cosine of x squared. So remember, negative times a negative was a positive. So that's why this is still, then we had positive of that times 1 is that, positive of this times this gives us this right here. Now, what can we do? Or what happens right here? Well, if you notice, we have a negative hyperbolic cosine sine, a positive hyperbolic cosine sine. These go. They cancel out. So that's nice. So what are we left with? We also have hyperbolic sine plus hyperbolic sine. We can add those are like terms. So we have 2 hyperbolic sine of x over 1 minus hyperbolic cosine of x squared. So there is your derivative. Remember, just take your time with the quotient rule. Write out that quotient rule, right, if you need to. What if we have, let's try y equals hyperbolic cotangent of the square root of 4 plus x squared. And we want y prime. Now remember, whenever you're deriving and you have radicals, what should you do with the radicals? Rewrite them in exponential form. This is actually the hyperbolic cotangent of 4 plus x squared. raised to the 1/2 power, right? Where'd that half come from? Because remember the index here, that denotes what the denominator is. If that was the fifth root of 4 plus x squared, this would be 1/5, right? Now, let's start taking the derivative. So we have to chain it, right? First to the outside, then the inside portion. Now the derivative of hyperbolic cotangent is negative hyperbolic cosecant squared of all this stuff. So we've only derived the outside component. Now we need to derive the inside, right, from the chain rule. So if I just block this out, how would you derive this piece right here? You have to do the power rule first, right? So we'd have to move that 1/2 out in the front. This doesn't change yet. Then we have to do remember we're doing the power rule, so what's 1/2 minus 1? Negative 1/2. Now we can finally get to we can derive this most inner chunk, 4 plus x squared. The derivative of 4 plus x squared is 2x. And remember, as you're chaining, it's all connected via multiplication, right? So let's simplify. So we have 1/2 times 2 is 1. That x, we can jam it out in the front with the negative. So we have y prime equals a negative x. And then we have the hyperbolic cosecant squared of 4 plus x squared to the 1/2. And what I'm going to do is, since this is a negative exponent, I'm just going to make it positive. Why? Because normally we want positive exponents. How do we make this positive? We flip it, right? So this is 4 plus x squared in the denominator now to the positive 1/2. And if you really wanted to take it a step further, we could convert these back to their root forms, right? Remember, if you have a fractional exponent, that's a radical, right? Remember what we did up here? I'm just converting back from this step to this step, right? Whatever that index is of that denominator from the fractional exponent, that's the index of your root. So I just went ahead and made this positive, right? It was a negative exponent. I flipped it. And then I converted these fractional exponents back into radical form. You could technically leave it like this, or you could even leave it like this right here, but this is not simplified, right? You always want to try to simplify it and make it look nicer. It looks a lot nicer in its ultimate form right here. This one, again, is equally valid. It's just we don't like seeing fractional exponents. So if you can, please convert these fractional exponents back into radical form. All right, so that is it.